by Vatsal, Saran from USC on using algorithms to understand transformers, using transformers to understand algorithms.
Thanks so much, David. And thanks to all the organizers inviting me and organizing this. I'm great being here. I'm Vatsal. I'll talk about some relationships between algorithms and transformers. And I'll start by just explaining the title a little bit. Like many of us, I come from a theory background. And the reason I really like theory is that it helps us understand the landscape of possibilities in many cases really well. So I think this is nicely captured in this image from the Simon's program on computational statistical trade-offs. Like any good piece of art, you can interpret this in many ways. Here's how I like to think about it. So the different axes here could be different resources, like running time, samples, memory. And all of these resources can interact with each other in different ways. There could be trade-offs between them, as depicted by these regions over here, I think. And theory can help us understand all of this at a bedside level without getting too lost in the details. I think that's one power which theory has. Maybe something like a compass to help us guide through this landscape. And it can also tell us what kind of algorithmic structures are needed to solve a problem in a certain way. So what algorithmic creatures reside in each of these regions maybe. So I'm very interested to see if we can use some of this understanding or this computational statistical landscape to understand models of transformers. And we've already seen some examples of this in this workshop, Daniel's talk, at least talk just now. So I'll talk a little bit about that. And then if I have some time towards the end, I'll also talk about if we can use transformers themselves to maybe explore this algorithmic landscape. And in particular, discover some algorithms for nearest neighbor search. See if I have time or not. It's okay if I don't. And with that, I'll get started with the first one. So let's start by talking about linear regression. So maybe continuing where our three left us. This is joint work with Dei Ching and Tianchi students at USC and Robin at USC as well. So transformers are really good at this setting called in-context learning. Many of you are familiar with this. Daniel talked about this too. So just to recap, I'll explain what I mean by this. So in context learning, you're given a bunch of examples, and the model should figure out the underlying task based on these examples. So here, English to French translation, and then figure out the label for this new example. And the difference from standard fine-tuning is that you don't update the model. So in usual fine-tuning, you get these examples, and then you update the model to make better predictions on these examples. In context learning, you take some model trained on a bunch of tasks or a lot of data, and then you just give it these examples. The model should figure out the task based on this context, and then make a prediction on this new example. And this has been one of the surprising capabilities of these transformers. They're really good at this. So how do they do this? Maybe a good starting point for this is linear regression, which is what was looked at in all of these works, very nice papers which inspired our work. So let's just look at linear regression. So linear models, so all of the labels will be given by linear model, no noise. What does this mean? And I'll describe the setup in more detail, but just to give a sense of what we're doing here, you're getting a sequence where all the labels yi are given by a linear model, w star to xi. So you get x1, you get the label y1, x2, y2, x3, y3. And then you get this new example x4. Think of this again like maybe examples from English to French. Then you get this new example, and you're supposed to make a prediction for this new example. Obviously, like this is linear system in 2 dimensions. There's no noise. There are 3 examples. You can just solve the system, and you know W, and then you can make a prediction. The transformers are really good at this. Like in D dimensions, they get pretty small error, which is the examples. And the question is, how do they do this? What kind of information are they using? What kind of algorithms are they close to approximating? And one hypothesis study in our course, which again inspired us, is that they are implicitly doing something like gradient descent. What do I mean by that? Again, I'll describe this in more detail, but just to get a sense of where we're going again. So you have the sequence, these 3 examples. And then you can define, say, the squared error objective based on these 3 examples. And the idea is that the model is doing gradient descent on this objective across different layers. So maybe in the first layer, you start with some initialization. Then you take a gradient step based on, like again, this square error objective based on the example, this context you had, continue taking a step with another layer and so on. So that's one way that models will solve this. And in this work, we'll provide evidence that in contrast to something like first order, transformers seem to be able to get much faster rates. We show that they can they solve the problem iteratively across layers and they match second order rates. I'll explain what these mean if you've already seen this, but essentially what we show is something like that. If you look at the behavior of the transformer across different layers, then it is very similar to second order methods in terms of the rate of convergence and the error as it decays over different layers. We look at this particular second order method Newton, but that the choice is not too important. So before I talk about these results in more detail, I just want to spend like 1 minute talking about the high level philosophy and the technique, and something you might call like applied theory. In the sense that the goal here is to understand how transformers are solving particular problems, this regression in our case. We have this big model, lots of parameters, usually over parameterized. One way you could try to do it is to maybe fit the model to the stars and try to inspect the waves, try to reverse engineer what the model is doing. But just because these models are so large, that can be hard. There's lots of possible solutions and there's lots of redundancies in the model. And one perspective we take is if we can use again this understanding of this computational statistical landscape to maybe refine this search. So maybe just by say looking at the input and output behavior of the model, can we say something about what the model is doing internally or what the model is not doing internally? Perhaps guided by what we understand about different ways of solving the problem and trade-offs between different resources and what these different methods, say first and second order methods, achieve in terms of these trade-offs. In particular, for regression, we understand theory behind it really well. So we know, say, information theoretical lower bound on the best possible rates achievable by any first order method. And remember that what we want to do in here is to see if transformers are more similar to a first or a second order method. We know the best that first order methods can do. And we also understand settings where this gap between first and second order methods is really large. So maybe we can use some of this understanding to design experiments which can help us see what these models are doing and uncover these mechanisms to some extent. That'll be the philosophy. Okay, so now let me try to get more concrete. I'll start by describing the setup. See the setting, pretty simple. So we're doing a linear regression. We'll have sequences of n examples. Every sequence of examples will have an underlying linear system W star, linear model W star. This will itself be drawn from some standard Gaussian distribution. And for every sequence, we'll also sample the covariance matrix for the data. For most of the talk, just have this covariance matrix be identity. So you won't really worry about that till the end. And then for each of these time points, for each I in 1 through n, we'll sample the data point xi from Gaussian distribution, 0 mean, covariance sigma, identity for now. And the labels will be given by this linear model W star that we sampled for the sequence. So every sequence is perfectly explained by linear models. So everything lies on this line and there's no noise. And for every sequence, there's a different linear model W star which explains the observation. Yeah, David.
Oh, sorry, just a question. So you're saying sigma is going to be identity for most of the problem?
Yeah, like for like the next 10 minutes at least, it'll be identity.
So it'll be super well conditioned, right?
Super well conditioned.
And then first and second order methods should be comparable.
They will be compared. Like the gap won't be as large, but there'll still be a gap, like in terms of second order linear convergence rates versus second order quadratic convergence rates.
Yeah, that'll be. Are you talking about first and second order in the optimization sense of number of iterations or
Yes.
in terms of number of standpoints?
The number of iterations.
And the number of iterations of the thing you believe tracks the layers, like the number.
That's what, yeah, that's what, yeah. So, so let's look at just to have us all on the same page. Let's look at different algorithms here and what they'll do. So say X is the matrix for the data so far, Y is the labels. So to solve this, you can just do ordinary least squares. If you have the number of data points as in dimension, you use the pseudo inverse, find the minimum norm solution. That's one way to solve the problem exactly. Then you have first order methods, gradient descent. You do your standard gradient descent updates on your squared error objective. And you can also do second order methods. So one, like we focus on the iterative Newton for the most part. So iterative Newton is just an iterative method to find an approximation of the inverse of the matrix. Essentially, you think of this as like doing matrix Taylor series. So like you're approximating higher, like more and more terms in the Taylor series. So you want to find the inverse of X transpose X so that you can do your OLS update. You start with this estimate just being the origin matrix X transpose X. And then you do these updates, which basically follow from doing Taylor series. And then at the kth step, you have this estimate NK of the inverse of X transpose X. You plug that into your OLS solution, and that's your iterative Newton update, iterative Newton estimate for weight vector. Okay, and let's look at these rates here. So for gradient descent, if you want to find an epsilon accurate solution, everything is well conditioned for now. You need order log 1 over epsilon iterations. Most strongly convex or conditioned. For the second order methods, you only need order log 1 over epsilon iterations. So it's exponentially faster. So again, the difference will be even larger in ill conditioned settings, but we just start with this. So, and then we want to see if across different layers, if transformers are behaving more like the first order method or the second one. Let me talk about the transformer setting a little bit more. So what are we doing here? We are training a model from scratch, just on regression. So we train a model on lots of instances on this linear regression problem, on the distribution that I talked about. And the model gets examples x1, labeled y1, x2, everything is d-dimensional, labeled y2, so on. And then it gets a new example xt plus 1. It needs to make a prediction y hat t plus 1 for the label y2 plus 1. And things staying on the squared error objective. And have all these in context examples. You get a new test example, you're making a prediction, and then you keep growing this one. Questions about this?
Is this the linear only transformer, only attention, or you also have a nonlinearity?
It has nonlinearity. So like I'll talk about some in the proofs, like we use some hybrids, but in the experiment we have nonlinearity.
No, in the proof.
Oh, when I talk about the proof, though, and so the theory will actually be a relatively small part, and that we'll use some hybrid where there will be some linear attention and there'll be some softmax, but I actually won't talk about the theory so. Like when we actually talk about the expressivity.
Training is just the usual.
Training is just the usual. Train on like square root.
Iteration of the second order method includes the iteration estimate of the reverse to the inverse.
So yeah, so these are just this is like say the for iterative Newton, the second order method, these are just the equations. So MK is your like at the kth step you have this estimate of the inverse and then you plug that in to get your estimate.
Is this one layer?
No, there'll be multiple layers. So we look at this like GPT-2 style architecture with 12 layers here. And then so like training a transformer, the final prediction will be given by a linear model applied on this final layer, this 12th layer. Okay, so we want to understand how transformers solve this across different layers. So train a model and then the final predictions are given by a linear model just on the activation, the representation of this final 12th layer. So to see what is happening across different layers, we train with these probes, basically these linear models on any intermediate layer to find that layer's estimate of the answer. So what are we doing here? We first train the model, we train the entire transformer using the squared error standard objective. Then you freeze the model and then you train these probes, basically just these linear models on the activations of the first layer or the second layer to try to map the representation, like the activations at this layer to the output. What is the best prediction that you can get using just what the first layer has computed and so on to the second layer and so on. So like at the final 12th layer, like this best linear model will already be what you learned during training time. But you can also train these linear models in any intermediate layer to see what those layers are doing and what predictions they are making. Yeah.
If you train on the info layer, would it just give it the answer?
If you train, it's a linear model, so it's actually just W transpose this. You won't get an answer. You won't get the answer because this is a fixed linear probe for all sequences, and all different sequences have different vectors W. So if you just train like you basically won't get anything if you train this probe directly at the input. Oh, so by doing this, we'll get like this plot which I briefly flashed before. So the x-axis here is number of in-context examples from 1 to 20 or so. Y-axis is the error on a log scale. And all of these lines denote the error of different transformer layers. Brighter lines denote later layers. And what we see is that the error goes down across different layers. So later layers are getting a smaller error. The transform is doing something iterative, but it's refining the estimated answer as you go from layer to layer. Yeah.
You have a 12-layer transformer.
Yeah.
The final layer is trained to predict the output.
Yeah.
But how do you get an output of an intermediate layer?
So to get the output of an intermediate layer, you have this trained model, and then you want to find the best linear model from the activation of that layer to like the output, the prediction space. So basically, you have the data distribution, and what you do is that you take lots of sequences from this distribution, and then you have the linear regression problem, where the covariates are the activations of, say, the first layer or the second layer, whichever layer you're looking at. And then the prediction is like the Y's are the actual labels. And then you're just training a linear model to map from these activations, these covariates, to like the prediction.
At every layer?
At every layer.
So this is different from how transformers are actually trained, right? Because usually you have kind of a loss with the last layer.
Yes, so this is after training. So you train the entire model, and then after training, we want to understand what the model actually did. So at the end of training, you're training like these different linear models.
So basically, like how useful the intermediate representations you've already found through learning are.
Yeah.
Right.
Yeah.
By training something that can interpret those intermediate.
Exactly. So this is just a way of interpreting essentially what these different layers are.
And just to clarify, when you're doing this, the weight of the transformer is fixed.
Yes.
And is it possible that you need information from previous layers to know what layer, like, not in the node would do, like, if you.
Yeah. Yeah, I think it is possible. I think like these layers are like, for example, like what the second layer is doing might be using something the first layer is doing. I guess what we are trying to see is in terms of these errors, like what is the best prediction that you can make, like using like the information at that particular layer.
Like, I mean, it could be that the transformer has, in all, including all previous layers, have even more information. Better prediction.
Yeah, we did try, say, training a probe which takes as input like the activation of the first 3 layers. That might be worth trying to. Yeah, we didn't try that. Yeah.
So for the intermediate layers, are you just writing the OLS thing?
For the intermediate layers, yeah, just finding the OLS solution to find the best linear model. Because that we want to find, like, interpret what is happening. So you just find this best linear model using like any solving the linear regression problem. Yeah.
Can you connect this plot to the first order, second order stuff? Because your x-axis is.
Yeah, not yet. I'll talk. Yeah, not yet. This is just to see that something iterative is happening.
No.
Yeah. Okay, so now like I want to connect to like say different algorithms. I need some metric to compare things so that we're just not staring at plots. So we use a few different ones. I think they give similar results. So I'll just talk about this one. Let's look at similarity of errors. So you have say 2 algorithms. This could be transformers with some layers, gains and with some number of steps. These algorithms given x1, they make predictions y1, a bar, and b for these 2 algorithms. And given the true label y1, you can look at the residuals that both of these algorithms get. And look at this for this entire sequence. Say up to xn, and then you have this vector of residuals for these 2 algorithms. And then we just take the similarity of errors of these two algorithms to be the cosine similarity between these two vectors of residuals. And overall similarity of the errors between these two algorithms will just be the expected cosine similarity over sequences drawn from this data generating distribution that I talked about. So we're just comparing like how similar these two algorithms are in terms of the errors that they're making. Okay. So with that, yeah, let me talk about the results that transformers are able to match these second order states. So this first part is something we already saw, and the claim is just to remind us that transformers are improving across layers, so they're doing something iterative versus say looking up the answer or something like that. They are improving across layers and defining this. That's the takeaway from this. Again, something we already saw. Now let's compare different algorithms, and the claim is that transformers are most similar to second order methods. So let me start with this. I'll start with the plot on the left, and there's a lot of things here. Let me just walk over them one by one. So the x-axis here is transformer layers from 1 through 12. I don't know if you can see it at the back, it doesn't really matter. Y-axis is steps of derivation from like 1 through 20-ish. And this is a heat map where all the colors denote the similarity between that many transformer layers and that many Newton steps. Based on this metric that I talked about, this similar cosine similarity of the residuals. Darker denotes a higher similarity. So what we see over here is this kind of a diagonal-like trend in terms of similarity between transformer layers and Newton. And I also have these like yellow boxes, which just denote the best matching best matching Newton iteration for a given transformer layer. So say the fourth transformer layer is most similar in terms of this metric to 5 steps of Newton, and that's why I color this with a yellow box. And what we see over here is there's some kind of linear-like relationship where each transformer layer seems to correspond to about like 3 or so steps of Newton. And at the end, it kind of flattens out, which I think goes back to what Atri was saying, that I think the transformer actually saturates, it doesn't get very small error. Now let's look at gradient descent. So the gradient descent seems to be like much more like exponential. If you go look at say the 4th, 5th, or 6th layer, they are similar to like 50 or so steps of gradient descent. 7th layer is similar to 200, then to like 700 and to 1,000 or so. So can you make sense of this? Maybe like going back to our convergence phase. So you know that here again, this well-conditioned setting, second order methods get this log 1 over epsilon convergence rate. Gradient descent gets a log 1 over epsilon convergence rate. So if you have a linear relationship between transformers and Newton, then you expect this exponential relationship between transformers and gradient descent. And if you just plot this on a log scale, like the plot with the gradient descent, then that exponential relationship is clearer because now you get a linear relationship on a log scale. So seems like transformers are able to match this rate second order methods, which are exponentially faster than the first order methods.
So here the heat map is about the angle between them. I mean, the log 1 over epsilon or the log 1 over epsilon, isn't this also about the magnitude of the errors? So
it's the similarity of the residuals, like if they are making similar errors. We tried like say other metrics, for example, instead of cosine similarity, you could just look at L2 or something. The problem is that then the errors become so small that you need to normalize things properly. Because for both of these, like eventually the error will become small. So if, in terms of, so I think like so you're asking if maybe if you look at say some other metric which is like say L2 distance, then would we see like something like this? Yeah. So if you look at something like that, then again you see same kind of behavior that you have a linear relationship between transformer layers and
it's still exponential on the other side, or
and you see something like you need a lot more layers. Usually exponential. I don't know if we actually did the heat map for like L2 distance, but like if it just in terms of the actual magnitude of the errors as well, you see the similar kind of relationship. So we also like did a plot where instead of looking at this cosine similarity metric, you just look at the actual errors and try to map that and compare across different algorithms. And again, you see the same kind of relationship. So different metrics seem to give like very similar.
Question, sir, with the error flow, how do you compare low level, low level, low level? Very confused because you have that error flow coming from transformer. When you say low, it's not easy to see how we low and low.
So I think, yeah, so that's a good question. So like what we're really saying here is that the rate matches the second order methods, which is like log 1 over epsilon. And seems to be exponentially faster than first order methods, which is log 1 over epsilon. We try to actually see if we can actually like just look at the error, decay of error and see if it's log 1 over epsilon. That turns out to be just messier because like the thing is that it's only a few layers across which we are fitting this, and actually seeing if it's like log 1 over epsilon or some other function, that I think like it becomes a lot more messier. So I think it becomes much cleaner if we just look at similarity between different algorithms and contrast the similarity. So now we can also so it's hopefully now we have this exponential relationship. You can ask if, for example, if you compare to some other first order method, if we could get a better match between transformers and that method, then we can appeal to like lower bounds that we know that we can't really improve on these rates without using second order information. So first order methods in general, they cannot get something much faster than this. So we kind of using theory to try to see what is not happening here. So they don't seem to be getting first order rates. And we can also use theory to like design settings where the gap is larger. So David was saying earlier, so you can use ill-conditioned instances. So there, gradient descent or all of its variants, they get a polynomial dependence on the condition number of the system, which is the ratio of the largest to the smallest eigenvalue. Whereas the second order methods, they can get a much milder polylog dependence on the condition, because they can use the curvature and correct for it. And in general, we think this is necessary, working theory side, which I'm interested in, where in general, we think that we cannot avoid these condition number dependencies using only linear memory or first order methods. And what this suggests is like a hard distribution to try to contrast these two techniques, first and second order methods. So we can have the covariance matrix, instead of being identity now, have DO2 eigenvalues at some large value, 100, DO2 eigenvalues at 1, and choose the eigenbases uniformly at random. So for every sequence, there's a different eigenbase. So now in this case, like we expect, like second order methods won't really get affected. So if transformers are similar to something second order, they shouldn't be affected. And we see something like that. Like if you look at the behavior of the errors of transformer layers across different layers, it's again similar to what it was before, and it matches something like Newton, which is also not affected by conditioning so much. So if you look at these green lines, it's still similar to 20 or so steps of Newton, and much faster than gradient descent, which is affected by conditioning and doesn't get as small of an error, even with 1,000 or so steps. And the heat maps also look very similar. If you look at transformers versus Newton, you see a linear-ish relationship, and more like an exponential relationship with gradients.
Sample the sigma here, or?
Yeah, for every sequence, we sample a sigma, but the eigenvalues are fixed, so those are not sampled. The eigenbasis is sampled uniformly. Yeah.
For testing is the same.
Yes, the same distribution. Oh, so yeah.
I have a question about your architecture. So,
Yeah.
The way you trained it is you had a transform architecture, and then in the last layer to make a prediction. Did you make a linear map from the attention heads like you're doing intermediate layers, or did you have like a usual because usually the way transformers work is you take an embedding and then you make a prediction head.
Yeah.
You didn't do that, right?
So it's just we just have a final like prediction head on the 12th, like the final layer to make a prediction.
Right, but what is the input to that prediction head? Is it the attention map or is it a final single embedding?
The embedding. It's the final single embedding.
Okay, so the transformer is trained in the natural.
In the usual. Yeah. So like so far, like I guess I haven't talked about theory yet, but everything so far is just standard GP2 train. So it's trained in the normal way.
So how you look at it, intermediate layer, right? Like how you look at intermediate layers is your own thing. Right?
Yeah. That is different, but everything else is trained in the standard way.
All right.
Have you tried the nonlinear function?
We tried some nonlinear functions. Like you see like similar speedups, but for like it's like for nonlinear things, like some of these gaps are also not clearer because both of these algorithms they become slower. But it could be interesting to look at more. You haven't tried it enough. Yeah.
What if the algorithms are
Yeah.
Because you're saying this gradient is central.
That's a good question. So things are, if you have different distributions, the test kind of varies on how far away you're going. If you go far enough away, then the transformer does not get a small error anymore. You could think of this in different ways. One is that it's probably not exactly doing some algorithm. So it could be that it's doing this something in distribution which matches this. And I think really what we know is that it's matching some weights. I think that's what we can really conclude. It could also be that maybe it's doing something algorithmic, but within the distribution, there are certain, like say, moments that it just like knows the value of the distribution, it's knowing, using those values instead of actually computing that on the sequence. Right. And those things break down once the distribution changes. But these things are not, they don't work as well when you go out of distribution. Right?
I guess in the previous sort of similarity figures, you're kind of saying like the left one looks linear, the right one's not, therefore left one's the right algorithm. Here, I guess it looks a little bit more like both of them are sigmoids. And I'm kind of wondering like, what is the right way to think about this? Because neither of them you would say are like perfectly linear per se, right?
Yeah, I think you still see something like pretty linear, like where, like again, I guess, like it seems like about like every layer corresponds to 3 or so steps, at least in the in-between thing. And again, the error saturates at the end.
Sure.
So you don't really get that small of an error. Versus like you need to look at many more steps to get the correspondence with
like if you zoom, like I guess you can't zoom in because layers are discrete, but like if you zoomed in on the left top, for example, would you see like an initial linear gradient descent region or something like this, for example? Like it's not clear to me that
it could be that in the beginning, like it could be that I think I think really it's possible that like even over here in the beginning it seems a little bit flat. So it could be that in the beginning it's something more similar to a first order thing in terms of the rates. And it's also like if we actually so go to the construction, what happens? So okay, just to say explain this first. So we saw this correspondence. So one thing you can ask is, can you actually implement something like a second order method? And we show this is possible with some modifications to the architecture in terms of changing the attention. So we show that we can match k steps of Newton with about k layers, so k plus 8 layers, and order d hidden units per layer. And that like corresponds to like this linear relationship that we saw between the number of steps and the number of layers of Newton, the number of steps of Newton and the number of layers. We like even the theory as well, we need this initial warm up and we need this final readout. Like so in the first few layers, nothing much happens in the construction as well. So it could be because of that, it could be because there's something different happening in the actual learned model. It's hard to say. And like it's also like we need order d hidden units, and that seems necessary. Like if you have less than this and you don't really get these fast rates experimentally, and more than this doesn't seem to help get you even faster rates empirically. Yes.
For more complicated problems, I mean, like L1 regression or linear programming, can we use this to get some insight on how?
What is happening internally? We haven't tried that yet. So I think like there are settings like so like in one of the papers that I mentioned before, they do look at like L1 regression, and it seems that models do get a small error. It would be interesting to see if we can say something about what is happening internally, because even for things like L1 regression, we also understand algorithms reasonably well.
Not only like what's happening internally, but we don't even know if we have the right rates. I mean, do we see if the rates from what we know match what the transformers?
I don't know. That would be interesting to see. Yeah. Maybe I'll skip this. So I guess one more question we can ask is like, what makes transformers suitable for getting, say, second order rates versus what? Yeah.
What matching you prove that gradient is
No. So this is an expressivity result. So yeah, we show that there is a construction which implements it in Newton.
What do you get on more? You need it for experiment?
Sorry, can I say that once more?
You said it's not also you said you did that for
Oh, like the first few layers are not getting
for the architecture.
For the architecture. The first few layers are not doing like getting smaller. Yeah, so they're just setting up some covariances and things like that. Yeah, you can ask, and there's some other work that shows some gradient descent convergence. So you can ask what makes transformers suitable for doing this, and like that's I think one nice thing about looking at structured settings like regression. You can contrast different architectures. So we looked at a recurrent model like an LSTM. So regions are not important. The main thing about this is that it processes inputs one by one. It doesn't have the entire context available to it. And we do the same thing. Probe different layers, see what is happening across layers. And what we see over here is that for LSTMs, things don't actually improve that much across different layers. They don't seem to be as iterative. And they actually seem to be very similar to something like online gradient descent. So if you look at the error, the orange line here, it's very similar to the pink line LSTM. And actually, the best way to see this, I think, is to see that they're actually forgetting previous examples. So what we do over here is that we give an input, we give as input some example that the model already saw in this particular sequence. And what on the x-axis, it's how many time steps ago you saw this particular example. If you saw this example very recently, then LSTM and OGD, they both get small error on this example. If you saw this a long time steps ago in the past, you get a much larger error. In contrast, for like a transformer, if you give an example which it already saw in this particular sequence, it gets a very small error. It seems like LSTM, like these recurrent models, because they're processing things one by one, they're forgetting previous examples. And maybe like it's because like these second order transformers, they have this entire context available to them. This additional memory maybe helps them implement and learn a more efficient algorithm. Because like work in theory also suggests that maybe like having more memory lets you get a faster conclusion. So I have like 5 minutes, okay. So maybe I'll like briefly mention one other thing. So in this part, we looked at models trained from scratch on this particular algorithmic problem. It's clear that in practice, like the data plays a very important role. What is the role of pre-training? So here we look at how LLMs do addition. Very simple task. And very simple setting, you just yeah.
So going back to the memory statement.
Yes.
So let's say transformer is like 1 parameters, but you only have like access to the past, but above the same at the same layer.
Yes.
Right. So let's say you compute something. So there's no way you can implement the next category because you have computed everything up to here. You cannot pass the information from here to the like on the layer.
Mm-hmm.
So I kind of see why using this one because it's having more access to the past memory rather than RNNs.
Yeah.
You're still missing the connection from the top layer.
The causal, because it's causal.
Because it's causally, but
yeah.
That's why I was wondering whether they thought about having kind of this kind of
encoder
layer embedding to like lower layer embedding connection will enable more network packages from computer.
That could be interesting. Like over here, I guess like even with with causality was enough to implement this second order method, but maybe there could be settings where you need something more like maybe like an encoder. We can talk more about it. Yeah. So like looking at like very briefly, just looking at how like again it's very simple task addition here. So we fine tune a pre-trained model on a very simple addition data set, sums of numbers. And just one thing important to note is that like we have each number be its own token. So digits won't be there on a separate token as in some previous talks. So the largest number, which is its own token for like GPT-2 here is like 500. So all our numbers will be smaller than 500. You train a model on this, it gets a very small error, not so surprising, the large model. And what you want to understand is how is it doing addition? Very simple setting, how is it actually do this? And we do something very similar, again, do these probes. So something also called logit lens. So basically the idea is that there's all of these residual connections in the model, like all of these attention and NLP blocks, they're making additive contributions to what is known as the residual stream. This is just the output so far. And the final prediction, as before, is given by this linear model applied at the activation of the last step. And what we can do is just take the same linear model. Actually, here we don't even retrain it. Just take the same prediction head on the output of any particular layer, or on the output of any particular attention or NLP block, and use that to understand the prediction at that stage of the model. So very similar to before. And so let's see what happens. This is again showing that there's some improvement across layers. I'll skip this. I'll go to this one, which pretty much summarizes the results. So we can just look at this and that'll summarize most of it. So the x-axis here is transformer layers from like 30 to 50 here. Y-axis is predictions in the logit space, like it's from like, I'm showing a subset of the numbers, like it should be a 0 to 500, I'm just showing 60 to 140 or so. So a heat map where the higher values denote the higher logit. Again, the way we get this is that we look at a particular, say, MLP block in this layer, apply this prediction here to see what the prediction of that particular MLP block is. So this is for this particular input, the sum of 15 and 93, answer is 108. We see that a lot of these MLP layers, they have a higher mass around this right answer 108. So a lot of red around here. It's maybe not so surprising. It's getting a very high accuracy. It should be able to get the right answer. What I think is more surprising is that we see these periodic patterns. So if you look at this particular MLP block, this is periodicity of 2. So it seems like that particular MLP block is guessing whether the answer is even or odd, solving addition mod 2. This particular MLP block is the periodicity of 10, so the higher values at 88, 98, and so on. So it's solving addition mod 10. And if you look at the attention layers, like you don't even see this general high mass around the right answer. All you see is these periodic patterns. And once you have this, these periodic patterns, like you can just you do Fourier transforms, and as expected, because you have these periodic patterns in the logit space, you see all of these spikes, like period of say 2 here for that particular layer, which has this periodicity of 2. Similarly, for these attention blocks, if you look at the Fourier transform, you see these spikes. And in general, this was for this particular example. If you look at average over all examples, do the same thing. Look at a particular layer. Look at the magnitude of the Fourier transform. So you take the logits, map to Fourier space. Look at the magnitude. You see all of these spikes in Fourier space at periods of say 2, 2.5, 5, 10, and so on. In addition to some general low frequency mass. And for attention, actually, you don't even see this like low frequency mass. All you see are these spikes at these different frequencies. So it seems like the way the model solves this addition problem is by using these sparse representations in Fourier space, where these low frequency components compute the magnitude of the answer approximately. What do I mean by that? Basically, like there's like a wave which has a high period, like maybe 250 or 500, which generally peaks at around the right answer, like 108 here, but it's not that fine grained. So these low frequency components get the magnitude roughly right. And then these high frequency components, they do classification, basically solve addition modulo P for some P 2, 5, 10. It gives you a much more finer range control, like whether the answer is even or odd, the last digit and things like that. And together you can get a much higher accuracy. So it seems like even though, so this model, like this task itself doesn't have any periodicity, it's just normal addition. Seems like the model prefers to solve it using these Fourier features. And we look at so basically, like you can see what these different modules are doing. And it seems like MLP modules seem to be doing more the low frequency part, attention is doing the high frequency part. And finally, like it seems like these Fourier features arise from pre-training in the sense that you just look at the pre-trained token embeddings of these models, like a lot of different models, they seem to again have these same spikes in the Fourier space. And if you train a model from scratch on just addition, you don't see these spikes in the Fourier space. So it's not using these Fourier, like a model trained from scratch on addition, same architecture, doesn't seem to be using Fourier features. But if you do this fun thing where you just take the token embedding from the pre-trained model and then train everything else from scratch, then again you see these kinds of Fourier spikes. Like it again seems to be enough for it to use these Fourier features, and that actually makes training a lot faster too. Like in some recent work, what we did is actually like just hard coding these Fourier features into the model instead of like training them seems to actually help in arithmetic quite a lot. So somehow it seems like models prefer to like solve this task in this Fourier space, and a lot of exciting work showing that some of these Fourier features seem to arise in different settings for different architectures too, even things like kernels and so on. Somehow maybe like they are a natural way to solve the problem, at least if you have the right data, and it could be something interesting to understand. Cool. I'll stop now. Thank you so much. I don't know. I feel like somehow there are lots of settings where they come up. So I feel like there should be some universality. So they come up in like in modular arithmetic, which maybe is not so surprising because modular arithmetic is periodic. But they also come up like in our case, they come up with normal addition. There's some work which shows that they arise as solutions to some max margin problems. And they also like come up with like image stars, like these like discrete Fourier transforms and so on. Somehow they seem to be natural representations for lots of different things. I think it's something to do with data because in our case they arise from the data clearly because when we came from scratch and we didn't really get it. Somehow like with natural data they seem like natural representations. Something which would be good to understand, but I don't really know what this means. I would be interested to know what it does. Yeah.
I'm still a bit confused about the first part of this.
Yeah, sure. Yeah.
Thing.
Yeah.
So if you are just mapping the activations with a linear function to the output, right? So then why would you not have zero? Like you suppose before you do any iterations, then this is the problem you want to solve, right? To find a linear, like that's what your linear equation anyway do. So if you right, so why would you not?
Why do you not have zero? So the main thing is that you're learning a single linear map, this probe, for every sequence. So every sequence, let me maybe go back to that. So every sequence has a different linear model which decides the predictions for that model. So for every sequence, there's a different linear model which decides what the labels are for that sequence. And this probe that we're learning, it's a fixed probe for all sequences.
Okay.
So like because like everything is random here, like just like with any fixed model, you're basically going to get dark. You won't get a very high effect. Like unless the model actually does something. So you have to So for example, if the model like actually has the right W embedded somewhere and then you can read that out, then you can get zero. But the model actually has to do that.
So are we trying using non-linear probes instead of linear probes? Does it change anything?
So linear probes already like so I guess one has to be careful to have the simplest probe because once we have like complex enough, if I have an MMP probe, then maybe just actually looking at the input as Arya was saying, then you might be able to solve the problem. So like in some sense you want the simplest possible thing. So linear was already enough to like get small errors. So we didn't try more than that.
So given this setup, I think you can easily check with classification stuff, like simple linear thing.
Yeah, I think Kanbuk had some work looking at like logistic regression where there was some like looking at this again the behavior across different layers. So and one could do this for different
Right.
yeah.
Because the same thing with y being a quadratic function. Like even that's pretty well understood.
Yeah.
Behavior of Newton, etc.
Yeah, and see what like so if I think it would be interesting. Like we haven't looked at like different like other functions and see like if models still do something second order versus first order. I guess like we generally like we want something where like, if we understand what the rates are and there's enough of a gap, then we can maybe see what the models are doing. So I think quadratic things also we could maybe say something.
So you probably have seen the figure that show the circular mapping for numbers.
Yeah.
This
Yeah.
So I guess it's kind of related to the figure.
Yeah. Yeah. I think so. There's some of this work I think which shows that like for things like dates, like transformers learn these circular things. Maybe makes sense. This periodicity. I think here we were.
And even if you just transformer from scratch,
Yeah.
you should data set. You might create values for numbers form of circular.
Yeah, so I think if you train a model arithmetic, then you see this like circular pattern. If you just train a normal arithmetic, like unless you train on a lot of data, it actually doesn't like. So we did that experiment too. You just train from scratch a normal arithmetic, it doesn't learn these Fourier things as easily. At least like there might be some blocking happening at some point. But it seems like pre-training is actually crucial. So with pre-training, it already learns, like the token embeddings already learn these circular patterns, and then you can do everything much more nicely. I don't know where this comes from in pre-training. Like it could be that there's a lot of arithmetic in pre-training, or somehow they are natural way to represent numbers.
Okay, I think, because even from our own paper, we hear that embedding actually emerge from scratch.
Even from
Even
scratch.
from scratch, bring on like television test path or that. Then embedding at some point form a circle.
I see, okay.
I'll share some of the.
Cool, yeah, we should talk more, because we thought at some point maybe there's some blocking should happen, but we weren't able to get that, but I would be surprised, yeah.
Okay, let's thank Vatsal again.